So everybody should be logged into Jasper and have copied over the workshop examples in this directory to their home directory and have changed into that directory. One other thing, Jasper is kind of slow right now for scheduling because it's very, very busy. I have created a test workshop cluster out of a few nodes. So you can right now log into that cluster and run the exercises when we'll be doing the exercises from there. So it's on node CL2 and 231. You should be able to log into there. And that could be as a secondary head node. So from there, a lot of these commands will be really quick to run, as opposed to take a long time to do. But you can only do this off of Jasper itself. So it's basically logging into a special set of Jasper nodes that I have set aside for users for this workshop. This workshop is two-part. The second part of this workshop is in a week, on the 18th of September. You really have to take both parts to be proficient with using the cluster and the scheduling system properly. The second part, of course, builds upon the first part. This workshop is using a cluster effectively scheduling and job management.
So excuse me.
Yes.
So it hadn't logged on to the to that subcluster, to the CL2 and 231.
You could not?
Yeah, I SSH'd it and I'm just waiting. It doesn't tell me anything.
Camille, it's beneath 230.
Oh, yes, sorry, 230. That's the 231 is, yes.
It's okay, it's okay. It's yours, okay.
231 is the machine that's actually running the scheduling software. 230 is the test workshop login node. Okay. So in this scheduling talk, we'll talk about job submission, scheduling theory, and troubleshooting. So for batch scheduling, on these clusters, when you're running jobs, it's via batch scheduling. That means that you're running as part of jobs, not as services. So it's not used when you need a service, for example, a web server that runs all the time, but preferred when you have one or more jobs, simulations that need to run, and you wish to get the results back sometime in the future. So this is not the cloud situation where you're running services. It's when you have some jobs to do, some discrete jobs, you want to put them onto a cluster and get the results back. And batch scheduling is much better for that workflow because your job is automatically started by the scheduler when there's enough resources available, and you get the results back, and you could get notified when your job finishes. So let's look here at a typical HPC cluster. So a typical HPC cluster has usually a very fast network, maybe InfiniBand, and a cluster management network. It has a login node that you could get into from the internet. It could have multiple login nodes. It usually has a machine that runs the scheduling software. maybe an administrative node, a whole bunch of compute nodes, and then some nodes that deal with file systems. So this is how a cluster usually looks like. This is pretty much an example of every cluster on WestGrid or in Compute Canada at the higher level overview. So what are the goals of scheduling? Well, when you run these jobs, your jobs have to be scheduled by a scheduling system. And there's basically three goals to it. There's fairness and policy. So you want the scheduling system to fairly allocate jobs and resources according to some policy that there is. As well as you want to have high efficiency utilization or throughput. So you don't want any resources sitting idle. You want, as a system, as WestGrid Compute Canada, we want every single resource being used by researchers. And the third goal is to minimize turnaround time. So to get your results back as soon as possible for you. Unfortunately, all three are contradictory. So we can only do it's only possible to maximize one, and there's trade-offs when you're maximizing between those goals. So fairness and policy, it does not mean everybody or every group gets the same usage. Unimportant science projects may get a larger allocation. Scheduler fairly allocates according to usage policy. With regards to efficiency, so when I say all resources that we want to be used, we want all the CPUs to be used at the same time as all the GPUs, all the memory on every node, all the disk I/O, software licenses, bandwidth. We would like to maximize the use of all those resources. Unfortunately, obviously, it's impossible to maximize everything. Some users may want to use more memory than CPUs. Others may want more CPUs. It would be impossible for all those resources to get utilized 100% all the time. And as you could see from that, there would be many gaps in the scheduling between jobs that don't utilize some of these resources. Of course, the third goal is to minimize turnaround time. Now, it's most important to users that use an iterative process to reach their goal. So if your workflow is that you run a simulation, you get the results back, you think about it, and then you submit another simulation based on the original results, then turnaround time is most important to you. If the system is set up to maximize resource usage, it may take a very long time for your job to run. That's going to be detrimental to users that have an iterative workflow. So it's always a balance between these three goals. So some insights. The shorter the wall time. So the wall time is how long, what is the maximum time that your job will be run by the scheduler. So the shorter the wall time for a job, the better we can meet the three goals of scheduling. So if all the jobs have short wall time, they're very small, they're granular. So you could think of like small pebbles inside a jar. It's much more efficient to pack them into the jar. It's also easier to meet the goal of throughput. It's easier for turnaround time because there's many more jobs that are becoming, there's many more resources that are becoming available all the time, so the turnaround time is less. So basically, the shorter the wall time of your jobs, the more efficient the scheduling system is. A corollary to that is that jobs that use large amount of resource per job results in a reduction of fairness, efficiency, responsiveness of the scheduling system. Of course, such large jobs are very useful to researchers as well. So it's all a trade-off here. Another thing is that the more nodes we have, the more resources we have, the better we can meet these goals. And I don't mean just more resources compared to demand. I mean, if we both increase the number of resources by 2 and the demand for the resources, because relative to the cluster, the size of the resources will get smaller, it will be easier for the scheduling system to get your jobs running. So that's the advantage of a large cluster. Large clusters are more efficient, more responsive, and more fair just by being larger. In addition to that, large clusters are capable of running larger jobs, expanding capability. But if the larger jobs are run exclusively, we lose the advantage of the large cluster. So if we increase the size of the jobs, just like we increase the size of the cluster, then we don't get the advantage in efficiency. So what does this mean? Well, basically, shared resources such as WestGrid are better and are used more efficiently than multiple small clusters. The larger the scope of shared resources, the better. So, a departmental cluster is better than one for an individual work group, but the larger and larger scope of shared resources, the better needs can be met for users, as well as improve the efficiency of usage. So let's visualize a single node cluster. Here's a single node cluster. So here's now, and this is going into the future 7 days. We see that a single node here with 4 cores. So are there any questions?
What's the difference between a node, a core, a CPU, and all these terms? I just want to make sure I understand this properly.
Okay, well, a node is basically a computer. So it could have anywhere between 1 core, in really old systems, to 2048 on, say, Honeybee, which is the largest machine in Canada. Your typical laptop right now is a quad core, right? Sometimes, servers can go up to 256 cores. Usually, we have a 2,000 core machine, which is pretty large. So that's what a node is. Core is a process. It's used to be a single processor, so it used to be 1 chip per core, right? If you had a Pentium 4, you had 1 core per chip. Since then, they've started putting multiple cores on the same chip. That's why your laptop has a quad core, because there's 4 of them on the chip. It's as if you had 4 chips before. There were servers with 4 individual 1 core chips. And basically, they've been all integrated into 1 chip, but there's still 4 cores. Is that satisfactory?
Yeah, and the core is itself the processing unit?
Yes. But it could be either, an individual socketed chip, or it could be one of many on a single chip. And I guess if you look back into the 1950s, they used to be spread across many chips in, old mainframes. So we could visualize running jobs on on this 1 node cluster here. So here we have 4 running jobs in blue. Some of them are going to finish in a fraction of a day. Some of them are going to take, 3 days and a bit to finish in this example. So let's say our scheduler has to schedule these jobs in order of priority. So we have a number of jobs here. You can see by their shape that some of these jobs require 4 cores to run. Some of these require 2 cores to run. Some of their individuals 1 core. And also by their length is the maximum wall time that the job will run. Also, I have numbered these 1 through 6, 1 being the highest priority job, 2 the second highest priority, and so on. We won't talk about how to get priority right now. Discussion about how the clusters use priority will be in the second talk a week from today. But this is how this system will schedule, the scheduling system will schedule these jobs in order of priority. Well, it's going to schedule the first highest priority job at the earliest time that it could run. Notice that it can't run today, tomorrow. It has to wait until halfway through day 3 to start running, until enough resources become available for the job to run. So the scheduling system blocks out this area to run this job at this time, 3.5 days from now. Second, it tries to schedule the second highest priority job. Notice that it could actually schedule it before the highest priority job, because it fits in to a location where the highest priority job did not. Then the third highest priority job, fourth, fifth, and sixth. So this is the scheduling system, how it's planning to run these jobs in the future. When the time comes for the job to start, it will start it, if nothing changes. But let's say that a job finishes early, it has crashed. Well, what happens at this point is that the next time the scheduling system tries to run an iteration and decide where jobs go, it notices that this job has crashed, and it starts rescheduling the jobs. First, it puts in the highest priority job, then the second highest priority. Notice that the second highest priority job is now running much, much later than it was originally scheduled to run. That's because the highest priority job gets to run first. And as a consequence, the second highest priority job was moved. The third highest priority job is then scheduled, the fourth, the fifth, and the sixth. So as you could see, all the jobs were rearranged in terms of when they were run. But they were always arranged in terms of priority. So always the highest priority jobs are scheduled first. Other things that could happen to the cluster is that somebody else could submit a higher priority job that would also rearrange what's going on the system. So I'm going to talk about backfill. So there is a command called showbf, and it tells you how many processors are available for immediate use by anybody, no matter what the priority and how long. This allows you to tailor your jobs to fit perfectly into the gaps left by the scheduler. So here we have, looking back, the original cluster, right? Which is a single node. So we don't actually see any nodes being available or any cores being available right now. But if nothing changes, somewhere in a day and a half, there's a gap on core number 2 that could run for, I don't know, 6 hours, right? So if in a day and a half you run the showbf command, it will show you that there's a core available on the cluster for a certain amount of time. This way, if your jobs can be made of a certain size, you could actually use this command, find out what holes are available on the cluster to run right now, and scale your job appropriately, and at that point it will run, no matter what the priority. You can have no allocation, and it doesn't matter because there is no other use for these holes, right? And we want all the resources to be used. So your jobs would run immediately. So here's an example of short serial jobs. Sometimes you don't even have to ask how long your job can run. If your job takes an hour to run, there's going to be a lot of holes in a scheduler, in a single core, of course, and not much memory. And you can have a lot of these jobs. Your jobs can fill in all the holes left behind by all the other users, which require much larger, more specific sized jobs. If you take advantage of that, you could get a lot of work done. So there's a few myths about running on clusters. So a big one is, if there's a large amount of jobs in the queue, my job will not run quickly. And that's not true. Because most of the time, these jobs belong to users with very low priority. And the reason why they have very low priority is because they are running a large number of jobs. So because they've been running more than their fair share, their priority is low. But because their jobs are easy to fill in into the holes, right, often, they are still running. However, your job, if you haven't run on the cluster, or your other group members haven't run on the cluster, will have higher priority than theirs and will run. So you should never, determine how busy a cluster is or whether you can run just by the number of jobs sitting in the queue. Also, most of these jobs may not be capable of running, as the number of running jobs per user is limited on clusters often. So there could be a whole chunk of resources just sitting there waiting for your job to run. But since we throttle the total amount of jobs that could run on the cluster by any user, your jobs could run immediately. So, right? So because of that, the cluster may have processes available. Another myth is that it's better not to submit many jobs at a time so that other users can run. Now, the myth here is because the scheduling system is more efficient if you submit your jobs earlier, as long as you don't go over certain limits. Because if you submit too many jobs, the scheduler may not have enough memory to do that. But that's a very, very large number of jobs. So if you're submitting, say, 10,000 jobs, maybe you should talk to us about it. But if it's less than that at any one time, then it's fine. And the fairness is ensured by the scheduling system. So the scheduling system itself will figure out when it's fair for your job to run. Now, how it does this and how you could look up this information, we'll talk about that in the second portion next week. So some tips. Make sure your job can run on the resources available on the cluster. So the scheduling system is wildly optimistic. If you ask for 1,000 gigabytes of RAM per node on Jasper, it'll let you schedule the job because it's optimistic that we'll install, nodes with a very large amount of jobs before your job will run. But in actuality, we only get funding every 4 to 5 years. So your jobs will never run, or at least not on Jasper. So you have to make sure that there's enough resources to run your job on the cluster that you're running. Also, look at the state of the cluster, accounts, and jobs to get more information on the system. And if the cluster is empty and you are able to run, you could run shorter jobs to evade the limits. So there's limits on how many jobs you can run on a cluster, but there's also limits on how many jobs and how much resources each of those jobs uses and how long they run. So for jobs that are shorter, you can run more of them than jobs that are longer if the cluster is empty. And that's generally true of most clusters, because most people put in limits so that no single user after a crash could come in and monopolize the whole cluster to the maximum wall time, which on Jasper is 3 days, but on Bugaboo maybe a lot longer. And now we're going to talk about some basic job submission. Oh, there's a question. What commands are necessary to see the information in the tips? So here I will. Along the links that you got, there was scheduler commands. And in here is all the commands that we discuss in both talks and how the output looks like and some highlights of some important information. Going over all the commands in detail is a large portion of the second talk in a week. But here's the list of them all. We'll use some of these commands, but for a thorough going through all the commands, that will be discussed on the 18th in the next talk. That's because a lot of these commands show information that is involved in how the scheduling system works, and we won't have enough knowledge to understand all that by the time we finish this talk today. So that's part of part 2. The other things that are really important is the PBS scripts. So here basically tables of how to run your job, all the PBS script commands. This is another one that you want to maybe keep and use for running your jobs later. Is there any other questions?
Hi, I have a question.
Okay.
How do you really define the wall time and the nodes and processors? What defines that?
Right. So when you're requesting jobs, you mean?
Yes.
Yes. Okay. So that's actually the next point that we're going to go through.
Okay, sure, no problem. Thank you.
So we're going to go through. We're not going to actually quite finish this point because there'll be. This is actually fairly involved, and we're not going to quite get to how to use memory and ask for memory properly by the end of this course today. That's the first thing we're going to do in the second part on the 18th. But we're going to start. So if you have a program, if you have a program that you wish to run and you need to figure out the resource requirements of your jobs. These requirements include wall time, which is the maximum length of your time your job will take to run, the number of CPUs, memory, nodes, GPUs that you need to use, and the queue, sometimes the queue that you are submitting to. The command to submit your jobs is qsub. Although the qsub allows you to submit your requirements on the command line, you should really put your requirements inside a job script, like the qsub job script of PBS example. So we have a question in the group chat, which somebody says, if I have a cluster, say 5 nodes, and each with 32 cores, and each core, that doesn't really make sense. With 8 processors, I'm not sure what the question is asking. 5 nodes with 32 cores, each core with 8 processors. Cores are processors. But the question is, do I really need to schedule it if for a reason I am only using only one node? The answer is, yeah, you don't need to. I mean, if you have a cluster, you generally want to schedule your jobs, because you may have a lot of these jobs and you want to schedule them one after the other. Or there could be multiple group members that each want to run on those nodes. So the scheduling system schedules your jobs after one job is finished, another one can then begin using those resources. It also figures out how to put these resources in a Tetris-like fashion so that there is enough to run larger jobs, if there are that in your group. Is there some more? Have I answered that question fully? Okay, well, that's it in the group chat. So here's okay. Here's an example of a PBS job script. So you start with what shell is supposed to be executing in a job script. Here we ask for one node with one processor per node. We have a maximum wall time of 5 hours. This is the wall time, the maximum your job can run. Another bit here is we could set up your email address so that you could be emailed when your job finishes, as well as the PBS, this command here, the setting, it sets when your job will email you. So when there's an error, before your job starts and after it completes. You could also name your job. And you need to CD to the PBS work directory. And then here's where you would run your job. So here's one of the tables for the basic job submission information, what it does and how to set it. So the A is when your job is aborted, B when it begins the execution, and E when it ends and the job terminates in here. You can also submit it to a queue. So if your scheduling system requires your jobs to submit to a particular queue, this is what you would have inside your PBS script. Okay, so we can now break for practice. So everybody should be logged into Jasper. Okay, we have a question. Is there a reason why we use PBS and not SunGrid engine? I guess PBS is more flexible, I believe. So here is the worksheet. So there are a number of so is everybody logged into nodes CL2 and 230? All these commands inside the worksheet can be done on Jasper itself, but Jasper is pretty slow because the scheduling system has to schedule a very large number of jobs. So sometimes it takes a while to respond. In your downloaded directory, there is a number of example answers. So it should look something like this. And you can actually see the answer to the first question. Yours should be a little bit different because you need to put in your email to be emailed. Please change this email into your email because I do not like getting a very large number of emails from everybody's jobs finishing. And I could track you down that way.
Hi, Camille. It's Vineet again. One more note. When we set up CL2N230 as our test bed, unfortunately, email isn't working quite properly, so you might not actually receive your emails. If you want to further test that functionality on small jobs, you can run those on the Jasper node directly, and you'll receive all those. You'll see what the output of all those emails will look like.
Yeah, and this is because node CL2N230 is inside the cluster and doesn't actually have an outside connection to the world, because it's just a temporary workshop cluster for this talk. There'll be a few questions later that you may want to get the results of an email back, but you can only test that on the Jasper cluster itself, not on CL2N230. And we're doing the first 3 examples in the worksheet. So right now, you should be running them. You submit your jobs like that. And then you should see the jobs. So right now, my job is queued, and then there's another user's job that's queued. So far, only one person other than me has submitted a job. And you notice here that they are still there, that they are in state queued. So the scheduling system runs every few minutes and starts running jobs. And when you run the qstat command, you could see all the jobs that are queued or running on the cluster. If you, on a bigger cluster, want to see just your jobs, you can do a qstat -u, and then your username, and it will just give you your own information. You could also do a -a for a bit more information. Somebody has noticed that there is no wall time set. in the answer to the first question, and that's correct. There isn't. There's a very short, well, there's a short default wall time that's actually added automatically by the system. Vast majority of the time, you actually do want to set it. And as you go on, you're actually supposed to set it in the second question. So in the second question, you're supposed to set a maximum wall time of 2 minutes and sleep for 200 seconds. Also, when you run your jobs, what happens when your job finishes is that you get two job, scripts afterwards. You get jobname.pbs.o file and then .e file. The O file is actually the output of your job running. So in our case, was just running the command hostname and sleep, and that was the host name that it ran on. Yours may be different when you run yours. And there's also an error file. And in this case, there's nothing in it. When you do a QStat, sometimes you see state C. That means that the job has completed. And also note that each of these jobs has a job ID. So each successive job gets a new job ID, as well as a job name, in this case, based upon your script name. Now, if you run your second jobs, did I run one? No, not that. Notice that in the second question, you're asked to run a job that sleeps for 200 seconds, but only has a maximum wall time of 2 minutes or 120 seconds. So two things should happen when your job runs. So here's my answer to job running. Now, it's supposed to be stopped by the scheduling system. Because you're running longer than what was asked for. What will happen is that there'll be an error inside your output file, and that if you are on a system that, like Jasper, that sends emails, you'll get an email message about your job being killed because it's run out of wall time. So we'll need to wait another minute for that example to start. Are there any questions?
Yes, I have a question.
Okay.
I'm wondering if I'm going to run a script, which I'm not sure about how long will it take and what's the maximum wall time.
Mm-hmm.
What should I set for that, for example, because I'm thinking that if I set something very large, it's going to receive a low priority for run. And if I set some time which is a small, I'm wondering maybe it's going to be killed before the processing finished.
Yes, that is the fundamental problem. You have to estimate how long your job is going to last, maximum wall time that your job will take. You will be, your group will get charged, not really charged, but your usage will be in. If you ask for a very long time for your job to run, the time that you ask for will be considered as you have used those resources for the purposes of your priority calculation. So you do not want to ask for too much longer than what your job runs, but the system needs to know how long maximally your job will run in order to allow it to schedule other jobs later, or to figure out whether your job could fit into one of those holes before another job is supposed to start. So you have to basically guess. If you're running a large number of jobs which are quite similar, you could run one job with a much longer wall time, see how long your job took to run. You'll get the result back in the email if you set up that job to email you when your job finishes. And then you could set the wall time for the remaining jobs. So if you have, say, 100 jobs to run, you could try one with a longer wall time, figure out a reasonable wall time for the rest of your jobs, and run those. Is there any other questions?
I have a question here. How do you determine the wall time basically? When you run a job, suppose I'm scheduling a job for probably 6 hours, but the job, and I have to play around with the nodes and the processors as well, right? So if you increase the memory and the nodes and processors, the running time will be decreased. So, once I run the job for 6 hours, it gets terminated because it exceeds that 6 hour time point. However, if I increase the nodes and the processing time, probably it will run in 4 hours. So, is there only a trial and error method to see what's the best combination to run a job, or is there a way you can really guess how much time it's going to need?
I guess it's trial and error and experience.
Okay. Okay, got it.
Yeah. So I had a question. How does the scheduler handle jobs when no wall time is indicated? Well, that's actually quite simple. There is a default wall time. So when we saw on the system your Q1, in the answer q1.pbs, where no wall time was specified, we see that the system by default creates a 1 hour wall time. At least the scheduling system on node CL2 and 230. Each cluster may have a different one. It could be like 1 minute. Because usually the people running clusters don't like users not asking for a specific wall time. There's a few machines which run single core only jobs. They may not have a wall time maximum clusters, but vast majority of clusters have a default wall time. So we here see that my jobs have finished. So we see that there is no output because the job slept for 200 seconds and never actually finished to to get to the point of writing out the host name. And we see in the error file that the job was killed when the wall time of 162 exceeded the limit of 120. So it took a few seconds for the scheduling system to figure out that the job had exceeded its wall time and to shut it down. In this case, about 42 seconds. And in the third question, we're asked to submit a job that has a name. So here's basically the script to do it. The name here is specified by the minus capital N and then the job's name. In here, we could see that the job name is now different. Previously, it was what the script name was, but here you could put in whatever name that you want instead of just the script name. It's often nice to, create a unique name so you could actually find your job. We could see the output of show queue. And the job info script. Oh, somebody's asking why we should use CD and then the PBSO workdir. So the reason we should use that is because you want to change the directory to the working directory. In other words, so that your job runs from your directory that you submitted your job from. Otherwise, the system doesn't know where, well, the system uses some default to run from where your job is run. So if your job script isn't there, or commands that you want to use, you always want to use that. Yeah. And of course, PBSO workdir is set by the scheduling system. So in this case, torque to the default where you submitted the job. A thing to note about the scheduling system, there's actually two parts. There is torque, which is PBS server, and PBS moms. PBS server runs on the scheduler node. PBS moms are what monitor your job on each of the nodes that are where your jobs run on. And in addition to that, there is MOAB, which actually figures out which job to run. So MOAB just figures out who's running and in what order and where. Torque actually runs your jobs. The question on can you set your output with PBSO workdir? I'm not quite sure. I'm not sure whether you could set. I don't think you could set it in the PBS directives. You could use it later to output. If you run some program and you wanted to point your output at that specific directory inside your program, you could actually use it. So if everybody is not have the chat window open, you really should, because there's a whole bunch of questions that are being asked and answered in the group chat window. So it'd be useful for everybody to look at that. Has everybody finished the 3 questions. Okay. All right, and I see most of the jobs that are done. Okay, so we'll continue from this point. So far, we've been scheduling very simple jobs. Simple one-core job and only one of them. But oftentimes, the advantage of using a cluster is that you want to use a whole bunch of resources and to run your jobs in parallel. Now, there's many different types of parallelism. Now, the simplest parallelism is running a whole bunch of serial jobs. Each of those jobs may require one node and one CPU, but you just have a whole bunch of them. That's actually a pretty efficient type of parallelism because there is no losses due to parallelism. It's very efficient. If, of course, your jobs can be parallelized like that. Another type of parallelism is MPI, which is message passing interface jobs, where individual processes communicate to each other via messages, usually over a high-performance network. So each of these processes or tasks requires one CPU, but could be on many nodes, or many times in the same node, or a few times all over the place. On the other hand, there's some parallel jobs, for instance, OpenMP jobs or Gaussian program, which is probably the most famous, which require that all the CPUs are on a single node. And of course, there's a hybrid one, which is an advanced one we'll discuss in the next slides. So in order to visualize these parallel jobs, we're going to use this as a basis. So this is similar to the single core cluster we had, except now we have 3 cores, and these jobs in dark blue are already running. So the scheduler never stops jobs that are running, or at least not on Compute Canada clusters. Once your job starts running, it will keep running until it's finished. And here's an example of how many serial jobs. So if you have 4 serial jobs, each of these jobs will be started independently. Since they're serial, they use 1 core, and they will finish at different times. And they'll finish quite quickly. So the last job will be done by the 5th day, but the end of the 5th day, but some of the jobs will be done by day 4 in this example. So many serial jobs are, the easiest, most efficient of the parallel types of jobs to schedule. They have an excellent scaling, so linear speed up. In other words, if you run 100 of these jobs, they'll run exactly, then you'll get 100 times more work done because there are just 100 individual jobs. So examples of this would be parameter searches, and you ask for a serial job in one of the following ways. So you could ask for nodes equals 1, processor per node equals 1, or you could ask for prox equals 1. When you ask for prox equals 1, you're asking basically for one processor anywhere. So here is a serial job example. It's like the ones we had previously. This one has a wall time of 5 hours. And here's where we're asking for a single core. So some tips for running more serial jobs. Try to submit shorter serial jobs. Many short serial jobs will run before a larger serial job or other type of jobs. So sometimes if you could break up your work into pieces, all the pieces will finish faster than if you asked for just one large, long job. For really long jobs, you want a checkpoint. So what checkpointing is jobs writing their output to a file, and then if something happens, they could restart from their last checkpoint. This way you could turn larger jobs into smaller jobs, or if you have really long jobs, for instance, the cluster may have a good chance of having a power failure or a hardware failure during that time, especially if your job is both very large and very long. If you ask for 1,000 cores for your job and want to run it for a very long time, there's a very good chance that one of the computers that composed the cluster or the 1,000 nodes that you're going to get is going to suffer a hardware failure. If you ask for many, many nodes for a long time, that's a pretty good chance. So in general, we like it's better for you and it's better for the scheduling system and efficiency to checkpoint your jobs. Now, another way of running serial jobs is called a job array. So job arrays are used when you need to submit a large number of jobs using the same job script. For instance, you're doing a parameter sweep. So there's a naming convention for job arrays, which is useful as you don't need to remember a large number of unique job IDs or job names. So here we have job name and then the array number. Job arrays are preferred as they don't require much computation by the scheduling system to schedule. So the scheduling system only has to, since they're all the same, only has to evaluate whether one of those jobs fits into a certain hole instead of all 100 in the whole job array. So it saves and makes the scheduling system more responsive. So you ask for a job array in one of the following ways. With the -t command, and you could specify a range, and this job array will, for instance, 0 to 99, and it will give you a job array with job numbers 0 to 99. You could also ask for a job array with indexes, and you can, also limit the number of maximum number of running jobs at a time. So for instance, if your job causes the file system a large number of that does a whole bunch of I/O on the file system, and the system the cluster cannot handle running so many of your jobs at the same time. This is how you would limit to running only, say, 5 of your jobs with the %5 here at the same time on the cluster. If you want to display information on a job array job and you want to use qstat -f, you have to put double quotes. And to get qstat to display individual jobs in a job array, you have to do a qstat -t. So here we have a job array script. Here's where we specify how many jobs inside the job array from 1 to 10, so there'll be 9 here. And here we use some PPS environment variables that are set. There's one set for job name, there's one set for job array ID, so which number of the job is it? The job ID itself, and of course, this is where it runs. So you could use this as part of your script. Are there any questions on job arrays?
So I didn't really get. So then we run the jobs below those lines. We just run our commands or different jobs below this lines?
This is an example Java array script. So if this script will be named something like myarray.pbs, and you would just queue sub it.
And how does it call the other? So do I save each one of these individual jobs in the arrays? Do I save them in another script, or do I just put them there?
So if you run this job, if you run the following example, if it was in some file, usually called sumfile.pbs, you would run this file with a queue sub. What would happen is that your job would end up getting a job name, which will actually be my job, right? You would get a job ID, which is some number, as we saw earlier, all jobs get, right? But not only would it be some number, you would also have something in square brackets. And inside those square brackets, you would have some job array ID. In this case, some number between 1 and 10. You would get 9 of these jobs in this example. If you wanted to run a parameter sweep, you could, in this point, generate some random numbers to fill into your job script to use, right?
Okay.
Did I answer your question?
Yeah, I think so.
Okay, we'll have an example of a job array. That's actually, I believe, question 4. Is there anything else? Does anybody else have any questions? Okay, I'll continue. So another type of job is an MPI job. This is a parallel job. An MPI job is a message passing parallel job. So each part of the job, each process in a job, sends messages to the other process. An example of this could be, say, a climate simulation, where each part has some part of the grid where it calculates the simulation, and then it needs to communicate what is the temperature at the edge of the grid. It needs to take this information from other parts of the grid and also get its neighbor's temperature as well. So that information is passed in messages by an MPI type job. Notice that the MPI type job, all the parts of it have to start at the same time. And but all those pieces can run on different nodes. They could be on the same node or in any other combination. Notice that these start later than, well, some of these at least start later than the many serial jobs. It also leaves holes in the system. The parts here where it can't start, so it's left empty. And the scheduling system is idle. These cores are idle until there's enough resources for this job to start. So MPI jobs use network for message passing, and oftentimes this network is a very fast network. On WestGrid clusters, it's very often InfiniBand. So for example, on the Jasper cluster, there's a 40 gigabit network, an extremely fast 40 gigabit. It's non-blocking and very fast, low latency. Each job uses multiple CPUs, each of which can be on different nodes. Each process has a different memory address space. So when they're running on different nodes, each process or task in your job cannot see the memory on another node. And it's much more difficult to write parallel code in MPI than OpenMP, because you could set up deadlocks, which are common. Now, what a deadlock is if we have 4 parts of your job, you could get into a situation where part 1 is waiting upon part 2 for information, and part 2 is waiting upon part 1 for information. If you're writing code, that's very easy to do. and then your job just stalls. So that's a deadlock. That's why it's more difficult to create MPI jobs. On the other hand, MPI jobs can scale higher than OpenMP because clusters are typically larger than even the largest SMP machines and also cheaper. So for instance, Jasper has 4,000 cores. Hungary, which is the largest machine in Canada, has only 2048. So a cluster with many nodes tends to have much more resources than even the largest machines in the world that are on a single node. So this is how you could do MPI job submission.
Excuse me. So now I got mixed up between MPI and the hybrid that you showed before in that table. So now we
Yes.
have an MPI number of, it's not only one CPU, it's many CPUs per node as well, right?
You can, yes. So the request, you don't care about where it runs. So
Okay.
you're requesting 64 processors anywhere on the cluster,
Mm-hmm.
right? Here, in this example, we requested 4 processors anywhere on the cluster. We didn't
Okay.
specify 4 on one node or on another node. We just
Mm-hmm.
told the scheduler system, please find me 4 cores anywhere on the cluster.
Okay, so what's hybrid then?
We'll get to later, but an example here would be, I would like 2 nodes, each with 4 cores,
Okay.
right?
Mm-hmm.
And you can actually specify your MPI job like that as well. Typically, you would specify it using procs because you want your job to be run as fast as possible, and you often don't care where your processors end up, on which node your processors run, right?
Yeah.
If you had some reason where you did care, then you could use the other specification and still run an MPI job. And this is actually topical with Jasper. So what's going on in Jasper with the newer nodes is that asking users to submit jobs which require the whole node, mainly because it's very difficult to run OpenMP jobs otherwise.
Oh yeah.
Is there any other questions?
I have a question.
Okay.
Suppose I have a job where I'm running a particular command and it gives me an output file, and I want to use that particular file for my next command. So how can I schedule those kind of jobs? Like what category they'll fall into?
So you want to run one job, and then based upon its output, you want to run another job that takes that first job's input and uses it, yes?
Yes.
Okay, so it's orthogonal to the category. So each of those jobs could be in different categories.
Mm-hmm. Okay.
What you want is a job dependency.
Okay.
And that will be covered in
next week.
A week
Okay.
from now.
Okay, sure. Okay. Got it. Thanks.
Okay. Anybody else? Okay, there's a question. Can I, in the group chat, can I run parallel jobs in one node? Is there a meaning of doing this? It seems to me that on one node, the best scheduling will be automatic. Yes, you can ask for all of one node. That's actually the next type we're going to be looking at. And yeah, there's advantages and disadvantages to that I'll get to. Is there any other questions? Okay. So here's how we run on a single node for multiple cores. So it's called OpenMP. Well, OpenMP requires this. And you basically ask for nodes equals 1, processes per node equals, and then some number, depending on how many processes per node are available. That's the maximum. So if there are 12 core nodes that are the biggest nodes, then the most you could ask for is 12. Otherwise, your jobs won't fit on any node in the cluster. So in a single node multi-core job, all the threads must run on a single node. The threads can share a single memory address space. And the advantage of OpenMP is that you could compile both serial and parallel code from the same executables. Threads are not the same thing as cores, but threads are similar to processes. So if you ask for nodes equals 1, processes per node equals 4, you're basically asking for 4 threads. Well, if you use the threads concept, threads are similar to processes. They're almost the same thing, but not 100%. There's a slight distinction, but in this case, this is how you would ask for a job with 4 threads. So OpenMP is one of the easiest methods of parallel programming, and it can be done incrementally. So basically, in OpenMP, if you have a regular C program or a Fortran program, and you have a big for loop, and that for loop is where most of your program spends its time, you can actually divide that for loop up into pieces and have parts of that for loop run on different processors as different processes, and you could parallelize your code like that. It's the easiest way to parallelize serial code. It's also probably the most limited way. You could also run MPI jobs by asking the same request. Nodes equals 1, processes per node equals 4. It's just that this is a more restrictive way of asking, because you're describing that you want that type of job request. You're requesting that all the processes are on the same node. So there was a question. So if I use prox equals 4 for, say, Gaussian job, wouldn't it automatically allocate the 4 procs on one node? And the answer is no, because what prox means is that it will allocate it anywhere. So usually on a busy cluster, it will find you the first 4 processors that are empty. And it's very unlikely that they'll be empty first for your job on the same node. It's much more likely that it will be 3 or 4 different nodes which will have empty processors, and your Gaussian job will be smeared across the whole cluster, and Gaussian requires that all the processors it uses are on the same node. But conversely, MPI, which doesn't require it, can use the tighter specification. So you can ask for all the processors to be on the same node to run an MPI job.
So if for example, I did this prox equals 4, and then it found, for example, 2 processors on one node, and then one on another node, and one on another node. Would Gaussian then use only 2?
No. Gaussian would try to run 4, and then depending on the scheduling system, either the scheduling system would figure this out and kill your job, or your job would stump over some other job, or if CPU sets were set up on that cluster, your job would stomp on itself, trying to run 4 threads on 2 cores and not succeeding very well. They probably wouldn't get the correct amount of RAM as well. So it would fail in some fashion, or if it didn't fail, it could be destroying some other user's job, in which case the systemints would find it and then kill it for you.
Thanks.
But yeah. So either way, please don't do that. So somebody's asking, what is Gaussian? So Gaussian is a computational chemistry program that's used by chemists and physicists and biochemists. It's a fairly popular program that has these strict restrictions. So the people that are making the Gaussian program were unable to make a parallel program that uses MPI that would allow greater parallelism and to run across many nodes. So as we said earlier, that OpenMP is the easiest method of parallel programming. The Gaussian people haven't figured out the algorithms to make that program parallel across many cores across a cluster. This is why, large shared memory machines are useful, because right now that is the only way that the Gaussian program can use a lot of cores and be parallelized. Oh, actually, I have a note that there's something called Linda, and sometimes it's possible to make Gaussian work across a cluster. But there's, in general, lots of programs like that. So for OpenMP job submission, this type of job must have its threads running on one node, and they share the same memory. So for OpenMP, the communication is done via the memory between different processes in a job. You ask for it like this. And one thing about OpenMP is that you have to ask the program to run the number of threads via an environment variable. So if you want 8 cores, you'd often do ONP num threads equals 8. But the best way to do it is to set it up. So you set ONP num threads equals, and then PBS num ppn. This sets your OpenMP num threads to be the number of processors that were given by the scheduling system. So what you asked in your job. That way you could actually change it in your job up, with this command, and it will automatically set the ONP num threads when your job actually runs. Yeah. So tips for running OpenMP jobs. Check the state of the cluster to see if your job will run quickly. If you need to run a large job, especially larger than what's available on your cluster, There's two WestGrid clusters called Breezy and Hungaby. So Hungaby has 2048 core machine, has a 2048 core machine. Breezy has a number of 256 core machines. So if you require an OpenMP job of that size, you should use one of those machines. You have to request those machines. If you have a number of OpenMP style jobs, you should consider running longer jobs using less CPUs per job instead. So there's some overhead in communication when you have a parallel job. If you have a very large number of parallel jobs, it may make sense to make your parallel jobs run longer, but use less cores, because then as a group, they will finish faster. But this advice may not apply when you need other resources, like a large amount of RAM per job. Yeah, so we have a few questions about Jasper in the group chat. So Jasper has over 400 nodes, 256 of which are basically have two socket, two hexa or 6-core chips in it. So 12 processors per node, and 160 nodes that have two quad-core or 8 per node, processors per node. The Jasper head node itself only has 12 cores, though. And a question, is a CPU core and a processor the same thing? Yes. A CPU core and a processor are the same thing. But a process is something that runs on a processor. So if you have a 4-process job or a 4-thread job, it could run on 4 different processors or cores.
Camille?
Yes?
Camille? So why does CPU info list 24 processors?
CPU info may list 24 processors because of what's it called? Hyperthreading.
Let's turn
So
off.
Intel processors can pretend they're 2 processors via something called hyperthreading.
So they're turned on, but we don't use it.
Yes, exactly. So hyperthreading is really useful for server workloads, not so much for high-performance computing scientific calculations. Basically, if you have a server, say, doing mail, a lot of the time it's spending waiting for disk. So it could actually pretend to be two cores or 2 processors, and then when one is waiting for disk, it could compute pretending to be the other processor. There's some IBM systems that could pretend to be more than 2. Some IBM power chips. But that doesn't help because there's not actually more more units that do the computation. So for high performance computing, where most of the time you're trying to get the computing done, it doesn't help. And in fact hurts because it takes some time to swap between that. So most clusters don't have hyperthreading turned on. We have another question. So how to define the memory used by each node and processor per node? That's actually the very first question we'll do in the second talk. Unfortunately, it takes too long for us to actually go through all the basics in one talk. It'd be at least 3 hours if we did so, because memory is a little bit complex. So that's the first part on the 18th. The questions in your worksheet actually go through those, and the answers are correct. And yeah. So the third part is a hybrid job. So you can ask for many nodes, say 2 nodes and 2 processors per node, or 10 nodes and 2 processors per node, or any other combination. And you'll get result like this. So depending on what you're asking for, it may run faster or slower than asking for all your processors on a single node, especially if you ask for 2 nodes and 4 processors in this example. In that case, they wouldn't start until there are 2 nodes available. So somewhere in day 3.5 on here, in this example, as opposed to our 2 processor per node job here. There's a question, can you choose which specific nodes to use? Yes, you can. There's multiple ways of doing that, depending on what you mean by specific, and they will be covered in the workshop on the 18th, right after memory. These slides are posted on the westgrid.ca webpage. They were also posted as a link could somebody else also put the other slides, including the PBS scripts and so on? Is there any other questions?
Sorry, all the slides are available if you slide to the very top of the group chat. Aaron posted the links to all of the.
And we've just reposted them again at the bottom.
Yeah. Okay. Well, the next part is, why would you use a hybrid job? Well, it's possible to combine OpenMP and MPI jobs for running on clusters of large shared memory machines, SMP machines. You may need more memory or other resource than is available per core. So for instance, if the minimum you could divide your job up requires, I don't know, 12 gigs of RAM, that's more memory per core than is available usually on our machines. So you may want to create a hybrid job. Also, there's advanced systems of running parallel jobs that can use resources more efficiently. So communication between jobs running on different cores of the same machine is much faster than running between distant nodes. And these systems use that to their advantage. So these systems include things like the Chapel language, as well as partitioned global address space languages, such as Unified Parallel C or CoArray Fortran. So they're special languages designed for parallel programming. They can use the fact that certain cores have faster communication to certain other cores than they do with cores across the cluster. So, they can run more efficient jobs, have less waste due to parallelism. And here are the table of the PBS script commands. There's this table is also of all the PBS script commands from both workshops, today's and the one in the week, is available as the separate PBS script PDF. And now we're going to go back in and try to run these jobs. So question 4 asks us to do job arrays. So we're going to do parts 4 through 9. When we have some extra credit ones, that means that they're the more advanced questions that not everybody would get the first time they run this, potentially. But the answers are there. So this is the job array example. We use a number of environment variables that are set by PBS or torque, including the job array ID, the job ID, the job array, and so on. So we would run the job like this. If we look through QStat, we just see the open square brackets. But if we do a QStat minus T, we actually see all the job arrays with the array IDs. If there's too much, you could just look at your own, you do a minus U, and then your own username. Yeah. In the fourth question, we were asked for a job with 12 tasks. And we see how it looks like. In show queue, yeah, it actually shows you the job with the job array IDs, each part of your job array that's running or it's queued. Only a certain amount of your jobs can run at the same time. Only 5 can be started each iteration that the scheduler runs. So these jobs are blocked. They will start to be run just as soon as the next time the scheduler iterates every few minutes, in this case. So in part 5 here, we do another bit. We limit the number of jobs to run to be 2 at the same time. So your job will actually be in a hold state until your first 2 jobs are run. You could limit the output just to see your jobs. You can do a show queue. And you see here for answer 5 that 10 of these jobs, or actually job IDs, the array IDs 5 through 12 are still queued, and 3 and 4 are running. So what happened is that job 753 array ID 1 and 2 had already run and completed, and now the second set of 2 are running. You could also, in part 6, specify job IDs. And you could list an array of job IDs, 1, 2, 7, 13. And here we see job arrays 1, 2, 7, and 13, the array IDs. So if you have some input number that you want, which is different for each of your jobs in a job array, you could use that as the index number. Are there any questions? Okay. So in question 7, we're told to edit start.pbs. Sorry, start 7.pbs. And yeah, you should actually edit it and try to run it with one processor. This is the MPI job. And you'll see the speed up. The other one could be run as the 4 processors. In this case, we're actually running an actual MPI job here as an example. In a lot of the other cases, we were just running hostname command when you were submitting the jobs and running them. In this case, we're actually running a real job. The first one, using one processor, should take a lot longer than using 4 processors. We could see 1 processor being used and 4 processors in the second one. That's the proxy equals 1, proxy equals 4. In a job info minus j, we could see the number of processors. In the show queue, we also see that. So these are all different ways to query the scheduling system about your jobs. We could also run the command called checkjob. This command gives you a lot of information about your job. You know, when it was started, that it's running, who started it, how long it's supposed to run, maximum, when it was submitted, you know, how many resources does it use. You could only check job your own job. You can't check job somebody else's, like mine. You have to check job and then the job ID for your own job. I can check job yours, but that's because I'm on administrative privileges. And in here, you'll see the resources used. You could do a -v if you want to have a lot more information. We'll be discussing how to look at your job and how to see a lot more information about your jobs in the second talk a week from now. So I suggest that everybody sign up for that one. And here we see which nodes the job is running on. This is a single core on this node. Yeah. Sometimes you may need to include the cluster name. Like that. Yeah. This command takes a while to go through and to understand everything that's going on there. But it's the greatest command for debugging what's wrong with your job. And if your job has a problem and you email support at WestGrid, the first thing that the support people will do will be to run that command. So it'll be check job, maybe with a few V's or not, and then the job ID name, sometimes the full name with the .cluster, right? So on Jasper, it might say, have a big long number, and then say .jasper. Except that it needs to be you must own the job to be able to do that, or be an administrator.
Camille?
Are there any questions?
Camille?
Yes?
Does check job only work on jobs that haven't run?
Yes. Jobs that are in exit state may not show information in check job.
That seems to be the problem with this 767. It's already done.
Oh, yes. So a user was having issues with running running check job on a job that had already finished. It needs to be either in queued state or running or blocked, but not have completed already. Another command you may run is qstat -f, which gives you similar information to check job. These are the detailed information on your jobs. Oh, somebody's asking why 760 didn't work, because 760 is my job belonging to user Camille. You can't run a check job on my job because you're not an administrator of this cluster and not me. However, if you run a job and get its job ID, you can run a check job on your own job. Answer to the question in the group chat. A question about deleting a job, so you could use the qdel command. So let's say I have a running job. I could do a qdel only for jobs which, of course, are mine. I cannot delete, well, I can delete your jobs, but a user without administrative access cannot delete your jobs. And that's how you delete a job. Yeah, you also have to specify a job that is still running for a check job. Yes, check job is a MOAB command, and MOAB takes the state of the cluster, takes information from the state of the cluster from torque every few minutes. So if your job doesn't actually appear inside qstat or check job, it may be because MOAB doesn't know about it yet, and you have to wait 10 to 15, 20 seconds until MOAB sees it. Also, MOAB sometimes can take a few seconds to respond, especially on a big cluster such as Jasper, which is really busy. And in this case, I can run this command on somebody else's job because I'm an administrator. Okay. Are there any other questions? Oh, so the question is, how do you restart jobs in a blocked list? So jobs in a blocked list are blocked for a number of reasons. We'll go over this in detail in the second workshop a week from now. There's many reasons why jobs can be in a blocked list. For instance, if you submit a large number of jobs, only 5 of your jobs are considered for scheduling because the scheduling system can only deal with, could only play, the game of Tetris with a certain number of jobs before it would be overwhelmed. So for each user, it's only the first 5 jobs. However, it runs every few minutes, so your 5 of your jobs can start every time the scheduler iterates. So we'll go over to the last so as part of question 8, we're asked to submit a job which asks for 1 node and 12 cores. It sleeps for 60 seconds and has a maximum wall time of 2 minutes. And then we'll look at it when we run it. So in here, we see that it doesn't quite show up yet, because show queue is a MOAB command, and MOAB takes a few seconds to run. And there we go. MOAB noticed the job and set it to running. Here we see it's using prox equals 8. We see here nodes 1, tasks 12. In this case, tasks mean processor. We can run the job info minus j and see we're using 12 processors. And we can run check job minus v and the job ID. And here we get a large number of information from a running job. In this case, 12 tasks on one node. And tasks means processor. Well, actually, you could figure out what tasks means. Resources per task, one processor, 256 megs of memory. So it takes 12 processors and 3 gigabytes of RAM to run this job. But it actually uses 0.28 processor when it's running at this time. You can see it got all in one node, node 229, and all 12 processors on the node. And there's a lot more information, like the job's priority and where it got it from, where the output and error files go, and so on. So this is how you would find out which node your jobs is running on. You could also do a qstat minus f, and it will also give you similar information, although not as much as check job. For a detailed discussion on what's happening and why jobs are blocked, that will be part of the second lecture, a week from today. And yes, this memory required is the memory per task. So are there any questions? So it looks like everybody's jobs have completed. Well, we've come to the end of our talk for today.